rather to say about contemporary, about current data conversion methods, and only mention about new.
新しい方法を持って最近使われている方法についてお話します。
Since it was only a short lecture, I won't be able to say everything what I would like to say, so I prepared some papers.
今日は今日の講演は短い時間でございまして、細かいことを全部言えないと思うので、今日は説明を用意してきました。
So after this lecture, I can give it to you. First is this is maybe most important. It is introduction to the data conversion methods. It is the title, the contemporary data conversion methods theory about applications. So maybe it's not very good now translation from Polish. So.
こんなふうに取りたいと思いました。一つはデータ思考のイントロダクションとしてポーランド語で書かれた論文なので英語の翻訳はあまりできないと思います。
Included is also listing of one of the most modern methods for data conversion, a source listing in C.
一つは一番モダンな方法の C プログラムリスティングをやりたいと思います。
And one paper maybe a bit more advanced about some method for conversion of textual data.
で、3番目はもう少し詳しいデータ仕組みを説明することが大切です。
To start the discussion about data conversion, I would like to first introduce to the divisions in this subject, to the subdivisions or subdomains of this subject to know more where we are.
初めにデータはどのようにどんなレベルに分けられるかご説明したいと思います。
Basic types of data conversion that are usually mentioned are lossy methods and lossless methods.
データは2つのタイプに分かれて、1つは lossy methods。損失のあることで、もう一つは lossless。ロスが原因ない方法です。
Usually, while a file or a data body is compressed, you want to get it back up during the process of decompression.
テキストを圧縮した後、その元のテキストを取り出したり、
These methods assume that you can lose some data during decompression.
ロスの方は、データは全部取り戻さなくてもよろしい。
A good example may be an image of like a photo, like an image of word that we sometimes don't need exactly the same image, or maybe better say when we don't assume that we need the same image, we can get higher conversion ratio.
例えばイメージを圧縮するときには、そのデータを取り戻すときは十分
These methods assume that exactly the same body of data that was compressed will be retrieved. So such types of data like fixed text files, like disk files, must be exactly retrieved after the process of decompression. I want to speak primarily about these methods as they are more popular now. However, to mention about this idea, I can say about such mathematical notion as fractal.
ラッシーの方も少ししたいと思いました。ラッシーの方はフラクトという数学的なコンセプトで説明したいと思います。
There is a very powerful method of compression, of lossy compression of images with using fractals. And we can get up to 100 to 10,000 compression ratio when there's a big image like a photo from airplane with millions of pixels. When such high compression ratio may be achieved with some loss of data, however, it's so high.
大きなイメージを識するときに、ワッシーの方を使うと、100倍から1万倍の圧縮が得られます。で、データは全部取り戻せませんけど、イメージの場合はよろしいです。
And here is a reference to an article about these methods. So,
説明の中にはこのメソッドについた参照があります。
now let us start discussion of lossless methods.
それからロスレスメトドの方を話します。
And maybe the best example or the best type of data to analyze is just textual data. So let us start analyzing a string of characters.
簡単な例はテキストです。
Let us assume that this is our body of data, and every character is stored within 1 byte.
この例では、この文章をテキストとして各キャラクターを1バイトで表します。
So, for this body of data, we need usually, normally, 1 byte times the number of characters here.
このようなテキストを表すためには、1バイトかけるの文字数の数字が必要です。
And for everybody, it's obvious that not all characters from the alphabet appear the same with the same probability or the same number of times in such central body of data.
こういう文章には見方が分かると思いますけど、アルファベットの全部の文字は出てませんし、全部のキャラクターは同じ確率で持ってません。
So the first idea to compress or to encode this type of data was to use shorter bit encoding for more frequent characters and longer bit encodings instead for less frequent characters.
初めの方法は、よく起こるキャラクターは、もっと短いビットコードを与えて、あまり起こらないキャラクターにももう少し長いビットコードを与えることでした。
So characters in our encoded data will be represented with variable length bit strings.
エンコードされたデータは可変のビットコードで表します。
So we need a method for representing variable length codes because here the length of the code is fixed at 8 bits. You don't need any special method to know what is the, where the code starts where it finishes.
最初の例で言うと、形新たに1バイトで最初のコードを出しますから、キャラクターとキャラクターのコードの切れ目が分かります。しかし、違うリンクスのコードを使うと違う方法が必要になります。
So now comes the notion of prefix codes. And
この方法はプレフィックスコードと言われています。
a good example of set of codes that are not prefix codes maybe this.
これはプレフィックスコードにならない例です。
These are variable lengths, and when we read a string like 0, 1, 1,
この例には可変のコードがあり、たとえ011のコードがあると、
then we cannot find out if it's 3 or just 2 followed by 4.
で、このコーディングシステムを使うと、011の場合には、これは3か2か4かが区別できません。
So these are not prefix codes.
ですから、こ
This
のセットはプレフィックスコードがありません。
and prefix codes may be represented by a binary tree.
正確なプレフィックスコードをバイナリーツリーで表します。
Let us assume that it is a binary tree. And here is code 1, 2, 3, 4. And the principle or the rule will be such that every left link will be assigned 0, every right link will be assigned 1. And then,
binary tree で prefix を表すとこのようになって、左リンクは0にして、右リンクを1にします。
So the codes 1, 2, 3, 4 get the bit encoding. Here is only 0. For 2 is 1, 0. For 3 is 1, 1, 0. And here is 1, 1, 1. Prefix codes may be represented by a binary tree, and this cannot be produced with a binary tree, this set of codes.
本当のプリフィックスコードはバイナリーツリーで表すことができて、最初の例はバイナリーツリーでは表せません。
So if, for example, these are letters like A, B, C, D, and we have text maybe BABA, it will be encoded in this way. First comes 1, 0, next is 0, next is B, is 1, 1, 1, and finally again A is 0.
今の ABCD に変えると、BABA のテキストをキャラクターの値をサブストして、こういうふうにエンコードします。
So for encoding data, we need a tree, and using this tree, every character is encoded. And while decoding, we can read this bit by bit, and using this tree, we can get going this way. Just when we get 1 on 1, we move here, and we get the D.
エンコードするためにはバイナリーツリーが必要で、エンコードされたデータをディコードするときに、このバイナリーツリーを使って文字を
The first program when it was set up in this domain was how to find for a given data an optimal binary tree.
問題になるのは、あるテキストに対するバイナリーツリーどういうふうにオプティマルなツリーができるか決めることです。
So the problem in detail is such that we have a list of characters in a given body of text. These are all characters, and frequencies of them are given or calculated. But we can, in this text first, calculate the frequencies. So it may be
あるテキストに出るキャラクターを調べて、キャラクターの確率を計算します。
And we want to build a tree, optimal tree of this type for this frequency.
キャラクターの確率を使ってオプティマルなツリーを作りたいです。
First solution for this problem was by Nagano in 1940s.
初めの方は60年代に社の方法があります。
same idea was such that we take this and try first to divide into two groups of modes, but when we calculate together the frequencies and divide it into two groups, these two groups are as close as possible to each other. So to find the best line of division of this into two groups, but this doesn't mean that we cannot change. We can select characters to group maybe 1 and group 2 in such a way that they are most close to each other. So here total weight is 14. So the half is 7. So we can put to this group, for instance, A, U, Z, and to this group B, C, D. And we start building a Shannon-Fano tree in such a way that all these codes are first put here and get one bit prefix 0, and all these get a 1 bit prefix 1. Now this process is repeated for every such group. So it is a recurrent process, and it goes as long as we have in every such group at least 2 characters. So until it is 1 character or until the code is unique. So in this case we get here A, this way, here U, Z, 1, 1, and this is finally U, Z, and here, because best partition here is 5 and 1, 1, okay, and here is 3 and 4, so however, this method does not produce an optimal tree. Because this partitioning is not unique. There are many methods of partitioning of such a body of data. So maybe we are making some error here that we took such a high values, what just we could here put not 5 and 1, 1, but for instance 5 and 2 alone, or just other selections will be possible for this. Also, this partitioning has complexity, not polynomial complexity. It's a problem is exponential complexity, so it is computationality density. Partitioning of a given set into two groups as close as possible is not polynomial complexity. It's incomplete.
ポリノミアルというのは多項式時間でないという、ではない。Not polynomial. Not polynomial.
There does not exist an algorithm with complexity that may be expressed by the polynomial of when n is number of these characters.
分割の数っていうのの増え方ですね。その増え方の複雑なコンプレクシティというシャープがあって、授業で公式の増え方ではないものすごく増えた。
For instance, solving quick solve has complexity n times natural logarithm of n. Yes, it's for quick solve, for another type of solve we get n square like insertion solve. It is proved that you cannot get for solving better than n times logarithm, natural logarithm of n. So these are polynomials. These are polynomials. It's also polynomial because it is less than polynomial. For matrix, finding the reversal matrix, its complexity is about n to 3 third power of n, and for best algorithm is n to 7 to 3. So,
例えば行列のインバースを計算したときにはコンプレクシティは n 乗から n の3分の2になります。3分の2になります。
Such algorithm, such complexity here does not exist.
このようなポリノミアルの ここに対する複雑さをポリノミアルでは表すことができません。
So one must use an algorithm of the complexity like n to n. So one has to use the algorithm of the complexity that is higher, it means e to the power of n. E? Algorithm of the complexity of this type. Well, n is number of 10.
ですから、E のn乗以上のコンプレクシティを持つアルゴリズムを使わないといけないです。
However, Shannon counterpoints are sometimes useful. Maybe also I should say that they are close to be optimal. Not optimal, but close to be optimal.
シャノンファンのプログラムはオプティマル
オプティマルではない。
シャノンファンの方が使える場合も多いです。
The first who found an optimal tree, binary tree, was Huffman in 1952.
オプティマルツリーを開発したのは D.A. ハッファン1952年に開発しました。
He found also a algorithm that which has the complexity linear, so n is the complexity of this algorithm.
ハッファンが開発された方法は n のリニアコンプレクシティを持つ方法です。
I can show how it works on this example.
さっきの例で言うと
First, we find two list frequencies.
最初に記述を持つ文字を選びます。
And we build a small tree of these two frequencies and give it the weight equal to the sum of these two frequencies.
でこの2つの確率をツリーにしてそのツリーのウェイトは確率を足したものです。
Then this process is again repeated. Once again, we look for two least frequencies and then we build a tree up until there is only a single tree.
でこのプロセスを繰り返して最終の確率を探してツリーを作っていきます。で最後に一つのツリーが残るまで繰り返します。
So this is the process I can assign for here is 9, here is 14. This process goes this way. And of course here we assign the zeros and ones. So for this set of data, this is a half-man tree, but it's also an optimal tree.
このデータセットに8万ツリーはオプティマルツリーになります。
And without proving, one can observe that in this type of tree, the more or the lower the weight, the more bits has a given character. It is here always true.
証明しなくて、ツリーを見てわかると思いますが、確率の低い個人は多くのビットなコードが与えられて、高い確率のオペレーターには少ないビットのコードが与えられます。
So it need not be true here. It is not always true here.
さっきの例で言うと、この方はいつもやられますね。
It's also only theoretical consideration, because for practical application, one must also include in this the method for storing tree itself.
これは理論的な考えだけで、実際にはこのツリーそのものをストアすることも考えています。
So we must, to encode this body of data, we must also ask have a tree structure, and to encode it also we must read the data two times. First to build the tree, and second to encode this data.
データをエンコードするときには、データを2回読む必要があります。最初はツリーを作るために、2回目はエンコードするために。
Modification of this dynamic half-man tree, but there's no need to read the data two times. We can read one time, and we also do not need to store the tree.
他の方法、ダイナミック
Dynamic half-man tree.
ハーフマンツリー他の方法ではデータを1回だけ読んでツリーはストアしなくていい方法です。
The idea is following that when we start, we can always consider data conversion as transmission of data. One is encoded on the other place is decoded, so we can write display or show our transmission channel. It is encoding. Decoding.
データらしく考えるというのはデータ転送のように考えてもよろしい。
And it's assumed first that every both encoder and decoder have the same, at a given moment of time, have the same half-man tree. So when a new character comes, it's first encoded with this tree, and sent as encoded data and decoded with the tree that is the same.
データが来るときはエンコーダーでハーフマンツリーによってエンコードさ
But at this time there is one new character, so we can rebuild our tree, like build it again for new set of frequencies. So at this time, when the next character comes, maybe this is increased, and we can build both encoder and decoder can build their trees.
新しいデータが入ってくると、そのキャラクターの確率が変わりますので、新しいパフォーマンスを作り直すことができます。
So, to consider this in detail, I can also mention about how to start this process of conversion this way.
それからはこの方法を使ってデータをそれからはこの方法によるデータ仕組みについて述べています。
There is a notion of so-called unseen leaf. Leaf, I mean, leaf is in a binary tree. When we consider it is root, it is node, and this is leaf.
データ仕組み使う場合の仕組みはアンシンリーフというものがあって、バイナリーツールは一番上のところはのルートと呼ばれて、その下にあるこちらノードと呼ばれて、一番下にあるのがリーフと呼ばれます。
So at the beginning, we can only the code for unseen leaf. Maybe let's say that's 1 bit 0 at the beginning.
初めには一つのアンシンリーフがあって、例えば0とします。
And when the first character comes, it is sent in this way that 0. This code of unseen leaf is followed by 8 bit of A.
で、一番最初のキャラクターが来るときには0、本当に0の後にそのキャラクターの1ビットコードを作ります。
When a tree is built in this way that the initial tree is built, that this gets the code of its code in Kaplan tree, and this gets the code of unseen leaf also in Kaplan tree.
最初のキャラクターが入ってくると、パフォーマンスを作って、この場合のコードとアンシンリーフコードを設定します。
So at a given, at any time, this looks like this, that we have codes for characters and a special code for unseen leaf.
エンコーダーは、データにあるバイナリーツリーはこのようになります。キャラクターが全部表すというで、その上にアンシンリーフのバイナリーツリーになっています。
So when a known character comes, known for the tree, like A, like B, C, D, it is encoded with this tree, and then the tree is updated. when unknown code comes, unknown character like E, then it is sent by sending unseen leaf. Now it is 111, followed by this code, original code, and then this unseen leaf is developed into unseen and E. So next time it may be already sent without unseen leaf, as it's with its half uncode. So next time this character may be sent without using unseen leaf, as its half uncode.
キャラクターが初めて出信されるときは、安心に心に自分のコードをつけて送られますが、2回目からは安心のコードで送られます。
Of course, with every new character, the tree is built again.
新しいキャラクターが入ってくるときに、ツリーは作ります。
However, there is very powerful method for updating tree when it exists. It is for when new character comes to rebuild, you don't need to rebuild the whole process, you only need to rebuild it with very short time.
方法があります。
It uses recycling property, and this method is described in this paper.
この方法はシブリングプロパティ、兄弟プロパティと呼ばれて説明の中に資料の中に説明されています。
Also, a modification of this method assumes that when a character is not in use for a longer time, it may be removed from the tree.
で、この方のバージョンは使われていないキャラクターが削除されていく方法があります。
So until now I discussed only methods that are based on Huffman algorithm or similar to this, maybe Shannon Fano or other like arithmetic words like transfer or
今まで出てきた方法は、ハフマンコードとスリムの会社のコードです。
And I observed that usually people know much about Huffman coding, but not much about more popular method that I would like to tell you now.
他の人はハフマンコードのことは大体わかりますけど、今はもっとポピュラーな方法があり、それについてお勉強したいと思います。
These methods usually are called textual substitution methods.
この方法としてはテキストセレクションメソッドと呼ばれます。
And the most popular of them is algorithm known as LZW from names. From names Lempel, Welsh, and it was invented, well, many modifications, you can say 1978.
This
algorithm is usually much better than Huffman coding. Also, there exists a dynamic version of this. And this method is also now mostly used because it is online method, and it's fast and powerful. You can do it once, then you can code it better. So how is it possible when before I thought that Huffman coding is optimal, how is it possible to get a better compression rate? Before we assume that we have only frequencies of characters. So, for example, such set is encoded also with the same number of bits if in the case when these characters are mixed. It's easy to notice that for such a body of data, well, probably exists much better technique than Huffman coding. So, Huffman coding is optimal when only sequences are given no information about the order of characters. This state of information about data is called in information theory a first order source. Means only information about frequencies.
First order source
Also, you can understand this that every character does not depend on previous characters.
のゲームもあると思いますが、各キャラクターは前に来るキャラクターに対応しません。
So when the characters depends on one before, we can call this second order sort. And also when on n-1 characters dependent, we can call this n order sort.
その前に来るキャラクターに依存するときには、一つ前のキャラクターに依存するときは、to order source ということで、n-1 までのキャラクターに依存するときは、n-1
And a good example maybe that when in our audio data we can encounter foreign data.
例えば、ハイテキストにこのストリングがあるとすれば、
It's most probable that the next letter will be O.
次は次のキャラクターが O になるのは非常に高いです。
So the idea of extra substitution is to get the gains of repeated sequences of characters, repeated strings.
Textual substitution methods は何回も出てくるストリングのパターンを認識する方法です。ストリングのパターンを使う方法です。
And the basic algorithm that may be called the extra substitution algorithm is the following. We have an area, it may be RAM memory, it is also called usually a dictionary, a local dictionary of our method, and it is also an area where we store our string patterns.
こういうテクスチャルサブスティションを使うのは、RAM にエンコードするためのテクション辞書を作ります。
So there are strings, these are strings,
それはストリング
and every string has an index. Let's say this is typical from 0 to 4096.
ストリングにインデックスがつけられて、例えば0から2090
So we need 12 bits to encode every string.
ですから、ストリングをエンコードするには12ビットが必要です。
And the idea is such that we, reading data, we try to find string in this era of string patterns. And when it is selected as this, and we have index of this, we send 12 bits index as that represents our string.
ストリングテキストを読むときに、
assume that this string may also modify this dictionary for future use.
ストリングによって辞書は変えられていきます。
Model of compression with this method will be following. First, we initialize our dictionary. It's necessary because at least we must have strings consisting of one letter. Because when we don't have string patterns, we cannot encode it in given body of data. So initialization usually assumes that we have 256 12 bits strings for 8-bit codes.
データを識する前に、ディクショナリー、辞書をイニシャライズします。で、最初にはストリングはありませんが、1文字のキャラクターを1文字のキャラクターを全部辞書に入れます。
And now start the loop. First is match. So finding the best match of a current we start at this position. So we are looking for the best match of this data to our string patterns. Let's see.
圧縮するときには、イニシャライズを終わって、ループに入ります。ループの最初のプロシージャーは、マッチというプロシージャーで、マッチでは、このストリングがすでに辞書に入っているかを調べます。
So just after initialization, we probably have only a single character and this text.
この例でいくと、イニシャライズの後、ループになって、辞書には N の文字が入ります。
So after the string is matched, this index is sent to the destination file or to the control line.
で、マッチのプロシージャーで、N の12ビットインデックス調べられて、それがデスティネーションへなります。
But next, after this character is sent, we have updating of dictionary.
N の文字がアップされた後に辞書のアップデートをします。
So, as an example, we can, when first match will be N and second match will be A, we have two characters, so we can build a string from these two characters.
2文字目の A が来たときには N と A の2文字のストリングができます。
So, this string will be added to this dictionary somewhere.
で、この NA のストリングは一緒に入れられます。
When the third character is read, we can add more strings and so on, and in this way, maybe longer strings. In this way, this dictionary is built as a dictionary of string patterns.
3文字目の G が来るときには3文字のストリングが を繰り返し作りやります。実証のストリングを増やしていきます。
And the longer the strings match, the better compression ratio is, because this length of bit encoding is fixed.
ストリングは長いほど圧縮に使いできないのは、長いストリングでもその12ビットの入力先が送られ
So at the beginning, this compression ratio may be not very good because there are not many string patterns, but after time, there are more string patterns, so it may be better.
最初は自身はストリング数が少ないので確率はあまり低くはありませんが、時間が経つと辞書は確率が良くなっています。
But after a time, this dictionary becomes full.
そのまま続けていくと辞書はいっぱいになります。
And we then must apply a dilation method.
ですから、ストリングの削除のプロシージャーも使います。
So we must remove strings that we think that will be not useful in future.
入れる場所を作るために必要なプロシージャーです。
And when there is a deletion heuristic, we call this algorithm dynamic.
デリーション、削除のプロシージャーがあるために、この方式をダイナミックと呼びます。
Otherwise, it is
そう、デリーションのプロシージャーのない方式はスタイルと呼びます。
static means that after time, when the dictionary becomes full, it is frozen and there are no more changes.
スタイルの場合には、辞書がいっぱいになってもなったらもう変わりがありません。
So, static algorithms are usually faster, but dynamic are better because they adapt and every moment of time they adapt to the data.
スタティックの方は早い方式ですが、ダイナミックの方は時間ダイナミックの方はよく適用できる方式です。
So, some methods we call adaptive as they adapt to the data being compressed.
こういう方式をアダプティブというアダプティブというのは適用できるということです。
Now, for this algorithm, we need three types of rules, of heuristic rules.
このアルゴリズムには3つのルールが必要です。
First, we must say what string is matched.
最初にこのストリングがマッチされたか
And it may be, as an example, the longest string, the longest number of characters that can be matched to this data.
データにマッチする一番長いストリングを選びます。
For update heuristic, we must specify which strings we want to add to this dictionary.
アップデートのルールでは、どのストリングを一緒にデータに
For example, when one method is possible such that when we have Nagano and next character is space, we select to be added the foreign string.
長野、そしてスペース、ストリングがということは、このようにストリングを選びます。
So next time, maybe this string is matched, and the next character will be U. For the next string added, and the second time will be this and U.
次に長野スペース、長野
U.
1回目は長野スペースで実際に入れられて、2回目では長野スペースで登録されます。
So probably after, if this method is repeated enough times, 17 times, 17 characters are in this method. So if it is repeated 17 times, it probably will be as a string in our table of string patterns, and it will be after this time represented with 12 bits.
このプロセスを繰り返していくと、17回繰り返すと、長野スペースユニバーサティが一つのストリングになって12ビットでインデックスで選ぶことができます。
Some update heuristics also assume that not one but more strings may be added to the dictionary.
あるアップデートルールでは、一つのストリングになって、いくつかのストリングが一緒に登録します。
Like Nagano is 1 following the letter, Nagano is 2 following the letters, and 3 and so on every time. Like this example, maybe not only one character, but 1 and 2 and 3 depends on the logic.
例えば、理由によって長野プラス1文字、長野プラス2文字のように登録されます。
Second is deletion heuristic to delete a substring image row.
次はdeleteのルールで、これはストリングを削除するルールです。
And there are many possible solutions. One may be that we remove this string that is least recently used. that has not been used the longest time. It was not used, but used means it was not much.
一つの方法はマッチされていない一番長い間マッチされていないストリングを辞書から削除します。
Another may be that the string that is removed is one that is least frequently used. The least number of times was used.
他の方法は一番確率の低いストリングを削除する方法です。
And now I can also show how works this LCW algorithm. It works in this similar way.
それから LCW の
Words area of 4096 street patterns. But every link is represented by every cell of this area stores one character only and link to previous string. As an example, when we have such words represented. Tail, the theater. There is some it is TAE store. So here is index, but it is only a single character. It has a link to previous character, previous until here is the
例えば、テールを登録するときにはこういうふうに箇所に1文字を入れて、でインデックスの最後の文字にポイントして、最後の文字から全部前の文字にポイントして、先頭の文字のポインターがつけられています。
when the next word is THE, we need HE stored this way. When there is a theater, we add 4 letters and these things. And finally, fields may be stored as here we have so just this. And this way is our table being built. So every cell contains a character and link to previous string.
このようにカプセルには1文字とその文字の前に来る文字のポインターが入っています。
And at the very beginning of this area, there are single character strings of A, B, C, D, E up to 256, just single single characters itself is a single character, it's also single character string. So when, for instance, we have in our data the following string, which is how the algorithm works, first, this single character is always found as a single character string here.
例えば、このようなストリングを一緒に入れたい場合は、最初のキャラクターを見て、最初のキャラクターは必ず1文字のストリングでディクショナリーに登録されています。
Then next character is checked and the system, the program checks if there is a string of A following T.
次に2番目の文字を見て、でその組み合わせが辞書になっているかをプログラムが調べます。
And since it is here, we are now here at the moment of time.
このプロジェクト、シークレットの組み合わせはありますが、ここまで切ります。
And next time we try to find all following each edge, but in this screen.
次にこの位置についてくるOを探します。
Then, since we cannot find here,
この場合にはありませんので、
this is our match at this time.
今回は TH がマッチとなります。
The index of this is sent to the destination.
このインデックス、それでこのインデックスが目的地へ送られます。
And the new string THO is added by adding O letter, so the letter O is added somewhere here and it is connected with it.
O の文字が辞書に入れられて、TH のストリングにリンクされます。
And then again this process repeats.
このプロセスを繰り返して、
Of course, when there is no room, some deletion heuristic is used.
文字を入れる場所がなくなった場合には、delete のプロシージャーを使います。
Also, while decoding this data, we get the same, very similar dictionary like this.
で、データをデコードするときも同じようなディクショナリーが作られます。
So, just after this index is received,
このインデックスが受信した後、
we can decode this. We can get this string from here. We can get these two letters as a string.
インデックスによってストリングが作られて、
And after decoding the next, we can add this string to the dictionary as a new pattern.
次の文字が 入れたらそれをディクショナリに
So this process is very similar like encoding.
ですからディコーディングの方のエンコーディングで
And I also have a paper here listing of a C program that does this method with index, extended index.
そのコースを10ビットのインデックスを使った C プログラムのソースを配ります。
So maybe this time is over this, so I will finish. These are papers that maybe need to be sent.
それでは何か質問ありましたらお願いいたします。This is not a question, but I have two comments. And the first comment is in the operating system Unix, complex and uncomplexed command use the, I think, rental regard.
Yes, I think so. I don't know about Unix, but most of these now used like these programs that are used for achieving are LCW levels. Maybe only Japanese man Kobayashi Yoshizaki has this version program. And which he uses some very strange adaptive coding, but not LCW method. For some type of data, he gets better results, but I don't know many details about his method.
日本語で脱足ですけれども、今最初の質問はUnix のコンプレックスとアンコンプレックスコマンドがレンタルシブルのアルゴリズムを使っているんではないかというコメント。And the second comment is, I read a paper that some people is developing LSI for coding and decoding LZ data.
LSI?
Yes.
LSI?
No, LSI.
Yes.
I have not. I cannot remember the correct title now, but I repeat the title of the paper at my phone.
Ah, yes. Maybe Dr. Hua is interested also. I have a reference here to one such LCI. I have 3 LCI chips, 2 for lossless methods and 1 for lossy methods. Chips are faster, they are very fast. This method is computationally intensive, so chips are very fast. Also, methods are used very advanced. These heuristic rules used are very advanced in these chips. So for these controllers for data transmission.
2番目のコメントはハードウェア化して LSI を作っているという論文を読んだことがあるというコメントに対して塚川さんはそれについて論文に同じような LSI の開発のハードウェアの開発の論文を紹介してあるというご返答です。
I didn't quite catch what point is new in your work. Most of your lecture is about language method, and I think the structure of dictionary is new, or is that true? Or
No,
what point is new?
until now there was nothing new. I
And I would like to ask you, have you got a new method better than number-seek method? For example, here Mr. Douglas have got slightly better method to compare to number-seek method.
Who was Mr.
And I'd like to know about a new method if you have got.
Maybe for me it's a problem to say about this because sometimes people claim that SW is better than half coding or so it's sometimes difficult to compare because I compress textual files better than LZW also. But to compare is difficult because sometimes it's different type of data and different way in which we read this data. So I assume that there only exist two methods, it's half-one coding and LZW coding. Now there are no more methods. When you have modification of LZW, it's only modification, and also it's more important maybe how you read this data. So when you say that there is a method newer than LZW, the first time I don't believe that it is something different than LZW. Maybe it's some modification, or what I will compare with because LZW are in many ways. So when given a body of data, we must analyze this. Check for some, I can show examples of data that can be easily compressed. For instance, when you have an output of a random number generator, LZW and any other method do not give any compression. But you can compress these bytes by using only this random number generator. So this is example that sometimes people have a body of data and use a tricky method and it's okay, you get better results than LZW, but LZW is general purpose without assumption of the data. And when you have more knowledge about this data, you can use this method in a better way. And without knowledge about data, I don't know about better methods when LZW with some special heuristics. These special heuristics are very many and very different. One is changing the length of these beats while encoding. When you have more repeated strings, you can use longer beats. When you have no repeated strings, you should use shorter, 10 beats, 9 beats only. So one method is changing the length of beats. Second method, upgrade to LZW, is a look ahead. Look ahead means that when you read text, you read a bit more of this text. And in this case, you can predict which string selection would be the best. Not just the longest match. I assume the longest match is not always true. Adding such string may not be profitable. Sometimes it's better to add something very different. Because when this is Nagano Union, for instance, we don't expect such string anymore. So there's also look ahead that makes this algorithm better. And when I say that new method, maybe I could say more about what are about very different approaches, like for dynamic half-one coding and also for method for text compression. Primarily I use these methods for text compression. So when we call something an alphabet, it is not everything that we can say about the body of data. We can look at such a text and see alphabet as words, not letters, but for words. And the method of new method is now also selection of the best alphabet in a given body of text. So we don't assume that it's the first given alphabet. Just select this alphabet, but maybe 5,000 meaningful codes, words, pairs of words, or two words together. So it is, but exactly new method is something not very, that does not appear very often. For me personally, there exist two methods, and third method is lossless limited encoding, but it's not powerful. So
yes, we have some questions. And now I'm doing about my research. It's about data compression, and I use the new algorithm that produce the compression ratio a little bit better than LampLC when we compare with the compressed and utility of Unix. But it's still some limitation and nouns on blocking and experiment. I want to ask you what about the LampLC, how to select the best substring, or how to parsing the string that gives the best or optimal compression, because there are many combinations of substring to select. Would you can you say that LampLC gave the optimal compression?
I think there are hundreds of propositions for this. So the problem is maybe that it's difficult to compare these methods. What do the best programs for achieving? They work in this way that they apply at the same time, for instance, 10 methods. This version of letter, this version, and they check which version is on a given body of data most effective. In this method is most effective for this part of the data is in this method. Then this method changes. So when I cannot say that this method is the best because this selection, because every time you can use this type of algorithm. Like there's such popular algorithm PKZ. And this uses a few methods. It checks the data, gets 10 kilobytes, checks 10 disks, and compares 10 methods. So this is the best we use this heuristic, this method. On every body, maybe this method is better. So when we consider general purpose, it's very difficult to select because we must assume something about the data. And I can also only suggest what may be the heuristic rules that may be applied. But since there are so many propositions possible, it's difficult to discuss it in such a way. Maybe I believe that you designed better method, but to compare it with LCW, you must take into account everything. For instance, the more complicated method when you need more time. Maybe these designers of Unix designed a fast algorithm. So, or maybe it's old version. I don't know what is the version of this algorithm, but because these algorithms are after 1980, most of these algorithms are ideas after 1985, before most of the algorithms were started without such heuristic rules. So I cannot just recommend some methods, but maybe I'm interested. I can talk later and see what's your method. Is it very different from SW? I don't know. Is it is it for general purpose or for a given body of data? I know one Japanese man is Kobayashi, I don't know, I know about him, his algorithm. And he gets on 30% algorithms better compression ratio than KZ. But difference is 10%, one on other side. So he usually is worse than this. I think this is top algorithm now. So in 70% he's 10% worse, but in 30% is better. But slower better.
他にこういうデータ圧縮の方法を論ずるときには、今、塚原さんが言ってられたんだけれども、その比較、どっちがいい方法かっていうのを比較するのは非常に難しいわけなんですね。でこういうアルゴリズムを紹介したときには、本当はそのバックになる確率モデルをきちんと提示しなきゃいけなくて、その確率モデルのもとに、これが一番いい方法だとかいうのは、本当のその最適性を論ずるときの順序だと思うんですけれども、その場合でもメモリーの領域の制限であるとか、それからプロセッサーの性質の違いとかですね、そういうものもモデルの中に入れなきゃならないんで、非常にその証明が難しくなると思うんですね。そういうことをやることが意味があるのか、むしろアルゴリズムだけいいアルゴリズムだけフォントとも発見的ヒロリスティックとかする方が、それはそれで意味があるのかもしれない。私はそんなふうに感じるんですけれども、後で彼には私の今言ったことを話したいと思いますけれども、他に向ければ時間が来ましたので、もうこのぐらいにしたいと思います。どうも長い間ありがとうございました。